Alright, so let me show you what that last homework assignment is going to look like, just as a preview. I'm posting that on Blackboard immediately after class. It's going to have two components. It's going to have one component where you're taking a watershed of your choice anywhere in the United States that's at least 1,000 acres, and I'm going to ask you to go through the process of subdividing that. I'll show you today how we can subdivide a watershed and run a HEC-1 model on it. And so this first part is kind of related to today's class. And then the second part of the assignment, the stochastic modeling, is something that we'll get into on next week. It's a way of kind of repeating simulations many different times to explore the sensitivity to uncertainty. So you can begin on part one of the assignment as early as this afternoon if you like, but then part two probably you won't be equipped to do that until we've gone over the corresponding in-class exercise. So that's going to be the next homework assignment. And then just to put it on your radar, our final exam is scheduled for the 1st of May from 8 till 10. And I haven't yet decided what that exam is going to look like, and so I'll hold off on giving you a description of how you should prepare and the way it's going to be administered, but I just wanted you to block that out in case you were planning to go somewhere great, you know, like on a big trip, and anyways. Friday the 1st of May is our final exam. So any questions on the announcements before we get into today's information on modeling a reach? Jeffrey asks about the finer details of the final exam. Yeah, I'll give you information about that next week. Any other questions on the announcements? Okay. Well, I sent you a file. Well, actually, I sent you an email asking you to download this file. So it's a zip archive. Hopefully everybody got that zip archive. What we're going to do today is we're going to open up this watershed and hurricane that we have looked at previously, and you'll notice that it said it was about 50,000 square acres. We're going to subdivide that just to get an idea of how to model the delay that water experiences as it flows through a stream. Because we've been so far just calculating the time of concentration of the watershed, and that time of concentration that we've been calculating corresponds to like overland flow delay. But even more significantly in many cases is the delay that water experiences as it flows through the main reach of the channel towards the outlet. And so this watershed is enormous, has a very lengthy reach, and we want to simulate the delay of the water flowing through the channel. And the location that we're going to subdivide is shown on the screen here. It's as Trace Fork goes underneath Clymer Creek Road, and I'll try and show you where that is. But if you're not very familiar with working with zip archives, the first thing that we need to do is right click on that and do extract all. Alright, and just wherever you'd like that file to be extracted, click extract, and now it's opened it up for us. And so you can see that I've got a subfolder here called Wednesday, April 15th. This is probably something you haven't done yet, but you'll notice that for my WMS file, there's a little icon that shows that it's associated with the WMS program. By default, .wms files I think are associated with Windows Media Player, and so there is a way for us to tell your computer that you want to open these files not with Windows Media Player but with WMS. And so let me show you how to do that in case you want to change the file association, because if you just double click on that file, that WMS file, when it's associated with Windows Media Player, then it will open Windows Media Player and give you an error message. It would be nice if you could just double click on the WMS file and it would automatically open that with the WMS program. So if you right click on it and then select Open With and then choose another app, then probably yours isn't saying WMS to begin with. Yours may already be saying Windows Media Player as the default. And so click on More Apps and then scroll down to the bottom. Look for another app on this PC. And then at this point you need to browse to the folder in the Program Files directory that has WMS in it. And so it's at the bottom of the list there, WMS 11.0. And so double click on that and scroll down the list until you find WMS 11.0.exe and select that and click Open. And oh wait, I think you want to check the box that says always open it with that certain file type. So we may need to close it and go back again, because unless you click the box that says always open it with that, then it doesn't reassign it the association. But in any case, you can always just open WMS and browse to that location and then open the file. It's just convenient if you are able to double click to do it. So I see the WMS splash screen here on my other monitor. Let me drag it over. It's opened up the watershed. Let me give you a moment to see if it opens on your screen as well. It's a pretty big watershed with a lot of data there, so it may take a few minutes to get loaded in. I don't want to go too far beyond until it's all opened up. Logan, do you have it loaded on your computer? Thank you. Cody, how about you? Great. I'll take that as an indicator that everybody's got it loaded unless I hear otherwise. And so if we just explore what data we have, just to make things a little bit simpler, since this is such a large watershed, it actually goes out, and since it straddles several counties, it went and got the soil data from 6 different counties, and it was a really huge soil data set, and it would have made that zip file over 100 megabytes, and I just wanted to cut down on the space and also cut down on the risk that someone has a technical error. So what I did is I went through the process of clipping the soil data and creating the soil type coverage. And so I'm already part way through the process that we follow in order to create a curve number. So you'll notice that we already have the land cover data, and that's what we see right now, that colored map where red is urban, yellow is suburban, green is rural and forested land. So we can turn that off as we like. I'll leave it off. It's just delineated as a single watershed right now, and if we switch coverages and turn on the soil type, then you can see that we have that complex series of shape files that defines the soil type for our watershed. And sometimes even when you're clipping the GIS shape files to create the soil type coverage, some of those polygons go beyond your boundary of the watershed, and so that's why it extends further south compared to where we actually need it to be. But the point is we have the soil type coverage, and we're going to be able to calculate the curve number when we need to do that. So let's just turn off the soil type polygons because that kind of slows things down. My computer's still thinking about it because they've just been displayed. So as soon as I get the little waiting icon, there it is, it's off now. So let's identify the point that we want to subdivide, because why would we subdivide a watershed? Well, one that's this large, we may get kind of an inaccurate view of what's really happening if we treat it as one continuous basin. And so subdividing can give you, number one, more control over particular hot spots that are more urban than others. Now, in this watershed, the development is pretty much evenly distributed across the region, but it could be the case in other watersheds that maybe the eastern part of the watershed is more developed than the western, and you want to capture some of that variation by delineating and having a separate curve number for each. So that's maybe one motivation that you'd subdivide, but then another is the hydraulics that we're talking about. Let's turn on the mapping in the background. So across the top, select Get Online Maps, and then let's use the World Street Map to try and find this intersection of Climbers Creek with Trace Fork. And I was looking at that last night, and I'm going to gradually zoom in on that location to give you an idea of where you should also be zooming in. Is there a question?
Yeah, Dr. Waite, I was just wondering if there's a difference between subdividing a watershed and creating multiple outlets and then just redelineating the whole thing.
WMS, that's a great question. WMS has a tool that I've never had a lot of work with, not a lot of luck, like where you can put in the maximum area that you want each sub-basin, and then it kind of automatically chooses where to put the outlets so that, you know, for example, this is 50,000 acres. If I told it I want no sub-basin more than 10,000 acres, then it can, in theory, say, well, then I know it needs to have 5 sub-basins, and it should, in theory, equally divide the areas by picking a good sub-basin location. But I've had some real screwy results with that, you know, like when you're having a machine choose where to put the sub-basins. And so what we're going to be doing to have a little more control is we're just going to place the outlet and we're going to redelineate over again, and it'll delete our existing boundaries. But with version 11, I haven't tried the subdividing where you set an upper limit for the area. Maybe they've got it working great now, but we'll do the thing that I know works, which is manual control over the outlet location.
Okay, thank you.
All right, so the location that we want to subdivide, I'm zooming in on that spot, and here we can see the map beginning to kind of match up with what we had on the previous screen. The text isn't as large as I'd like, but if we go into the wizard and jump down to choose outlet location, we're going to drop our second outlet because the first outlet's already there and it's going to stay there. But the second outlet we want to drop is right where the stream goes underneath the road. Alright, so you create that outlet, and then we're going to click Delineate Watershed. And so for those of you who maybe don't know, the question that we were just talking about has to do with subdivide basin, where you can put in a maximum allowable area, and then in theory WMS would automatically divide it for you. And maybe that's something we can play around with if we have some extra time at the end of today's class, or it's something you could take a look at on your own time. But I've never been bowled over by the accuracy of those results when I've done that. So that's why I dropped this outlet in a spot that maybe I was interested in what's happening at that bridge anyway, because it'll give us a hydrograph for the flow at that location. Alright, so click Delineate Watershed, and it's giving us the warning message that everything we've done before is going to be deleted. If we had, for example, curve numbers calculated or time of concentration calculated, all that will be wiped when you redelineate the project, and so we're going to have 2 outlets rather than just 1 that we've had previously. So click OK. And it takes a moment to think through, and It's having to calculate the flow distances, which can be a lengthy process. Alright, and then here's the result. I'll turn off the map now that I don't necessarily need that. So we have two watersheds. One of them's 21,000 acres, one of them's 27,000 acres. If we go into the hydrologic modeling module, we can see kind of the schematic structure of our watershed. There's the east basin flows to an outlet that here is called 4C. And so 4C is where all of the flow collects. And then the flow from 4C goes through a reach. And so the blue line that's connecting 4C and 3C represents a river. Now, in theory, what WMS is assuming is that until the water gets to 4C, it's not in a river yet. Or at least WMS doesn't have any way of simulating the flow through the river. Now the reality is it's definitely in a river, like in reality on the ground. If we went out, the river would extend many miles upstream of this 4C location. But 4C is the first place where we would be able to define the channel characteristics, like for example the shape of the channel, its slope, the roughness value N that would go into Manning's equation. All of those hydraulic parameters we're going to define for the reach that connects 4C to 3C. Alright, so we have two basins. Let's now calculate the curve number for each of them. And so we can do that by opening up the wizard again, going down into I think I've already done the land use and soil data. I joined the tables like when I created the soil type coverage. This is maybe the first time that you've had a soil type coverage already given to you. So we're interrupting, like we usually have a two-step process for calculating the curve number. The first step being creating the soil type coverage. We can skip over that because we've already got it, but we're going to go into hydrologic computations and then compute GIS attributes. We're going to again need that curve number table that I've shared with you before. So I'll have to browse to find that. So it says that it's going to use the soil type coverage for determining soil type, and it's going to use the grid, meaning National Land Cover Database, for the land use. But now let's browse to a location that's showing that soil. I think maybe I have it in, there it is, my subfolder from Monday's class. So get the curve number table in a location that you've got it, and then we can see it's reading in all of the soil types and land use descriptions. Click OK, and then it will calculate the curve number for each of the subbasins. And the report that it gives us in the notepad has the data for both of them. And since it's such a large watershed, there's quite a lot of individual entries where it's calculating the area for each combination of land use and soil type that it's got. So basin 3B, which one was that? Was that the 3B is the west basin and 4B is the east basin. So 3B has a curve number of 68.9. 4B has a curve number of 69.4. Okay. Now hopefully your curve numbers are in that same ballpark. I don't expect that they'll be exactly the same necessarily, but it should be pretty close. Now that it's calculated the curve numbers, those would be pasted into the fields that we need to calculate the time of concentration for both of the basins. And so let's compute DC using basin data for both of the basins and choose the SCS method for each. And you'll see that we have the watershed length defined, the curve number is set, we have the watershed slope. Alright, and so it's calculated the lag number of 2.5 hours here, and then it converts that into a time of concentration by multiplying by 5/3. And then we'll do the same thing for the other basin. Basin 4B is the one in the east. It's the upstream basin. Calculate with the SCS method. Alright, so we have a lag time for each basin. Click Next. And let's actually close the wizard at this point. And in the hydrologic modeling module, we're going to open up one of the individual basins so that we can define the precipitation for it. And the way to do that is you have to double click on the brown icon for the watershed. And sometimes that's hard to do when the text is on top of the icon, but if you just double click on one of the basins, then it will open up this Edit HEC-1 Parameters dialog box. You may have to zoom in a little bit before you have an idea of exactly where that is. You can double click on. Sometimes I get in the habit of moving the icon out of the way so that it's not on top of the text. Of course, we can turn the text off. In these display options across the top, you have control over the data that it's showing on the screen. So for example, right now it's showing the area and curve number and the units. I could switch all of that off if I just wanted it out of the way, and then it's not an issue anymore. And I still know that data. I haven't mentioned that over on the right hand side of the screen we have the properties for the watershed that's being selected right now. So if we go into the drainage module and select this basin, then it will tell me the information about the basin, like its area, basin slope, maximum flow difference, distance. I think AOFD is average overland flow distance. If you click on it, then yeah, down here at the bottom it gives you a description of what that is. And so I could click on the other watershed and then it gives me the similar summary of the characteristics of the other one. So the point is we don't necessarily have to have these display options turned on, but I mean, I guess sometimes it's nice to have this data, you know, the curve number, basin area, units, and you can turn it on if you like it to be there. But the reason why sometimes it's convenient to turn it off is that the basin icons are in the same spot, but you can always move them out of the way. Alright, so let's open up the East Basin and give it some precipitation data. Alright, so we will use basin average, meaning that everywhere in the watershed has the same rainfall depth. Get precip from web will allow us to choose, let's select the 10-year storm, click Get Data, and it goes to the Precipitation Data Frequency Server, identifies the mean rainfall depth for a 24-hour storm. It will get the 90% confidence interval. It's just going to use this mean value. So click OK, and then we have to define the temporal distribution. And this is where we go down and select the Type 2 24-hour storm. Click OK. And then OK, and it fills in all of that rainfall depth information for the steps that we're going to be using in our simulation. And we can just take a look at the loss method. It's using curve numbers to determine how much flow goes into the soil. Okay. Unit hydrograph method, it's using the SCS method based on the lag time that we calculated earlier through the wizard. So that's good. Okay. Now, the next hydrograph station button across the top, let's click that and skip over, not to the reach quite yet, but let's just go to basin 3B and define the precipitation in that basin. So you can see now down in the little summary window, it's really small and hard to see, but this is basin 3B, and if we bring up the basin data, we can verify that, yeah, this is basin 3B that we're looking at. And so let's define the precipitation again to be the basin average, get precipitation from the web, choose the 10-year storm, get the data, OK, define the series with the type 2 24-hour temporal distribution, OK, OK again, and now we're done. So you can click the Done button, and we're ready to run the simulation. So before we do that, did anybody get stuck at a certain spot or need something clarified before we run the HEC-1 model? Alright, so if we're in the hydrologic modeling module, then the menu across the top will have HEC-1 as an available option. So click that, and we want to run simulation. And it gives you a chance to specify where to put the output files. And these output files that it's creating can be opened with Notepad if you're ever interested to look at actually what kind of a text file is being generated by HEC-1. WMS reads this output file automatically, and that's where those hydrographs come from. So, you know, WMS is a pre and post processor, meaning it sets up the model and then it reads the model output, but you still have the ability to look at these output files, and maybe we'll do that, but let's just see where it's going to put it. It's going to put it in, I'm going to tell it to save it in Wednesday, April 15th with soil and land. So it'll go there, and then click OK. And when it's done, we will get runoff hydrographs in several different places. So let me explain these different runoff hydrographs that we're seeing, and we'll open them as well. So the hydrograph icon that's above 4B is just the runoff inside of basin 4B. And if we double click that to open it, maybe I need to zoom in a little bit here. Oh, it opened it on another screen. It was opening it all along. It was just... okay. Alright, so what it's showing me is the effect of this storm. It was a 10-year storm, and the time to peak is 915 minutes, and the flow rate at the peak 4262 CFS. So if we open up the hydrograph at 4C, it should be an identical hydrograph. And let me open that, and it opened in the other window again. I'll bring it over. So it's the same. It's the same peak depth. Let me open the first one and just drag it over to be sure. So the basin and the outlet hydrographs look the same. This is just for the east watershed. And the reason why is that, remember what I said is that WMS doesn't know any hydraulic characteristics for what's happening in the east basin. But what we can do is we can tell it some information about the reach that connects 4C and 3C. So before we do that, let's just take a look at basin 3B, the hydrograph for that one. So here's 3B, a peak of 3589, but when I open up the hydrograph for 3C, it's going to be quite a bit larger. So why do you suppose that the hydrograph for 3C has a peak of more than 7,000 CFS, whereas the peak of the basin that it's connected to is only about 3,600? Well, it's because this hydrograph is combining two hydrographs together. It's combining the output from 4C and the output from 3C together. So what it's doing is it's combining two hydrographs. So this hydrograph, the one on the left, is the combination of, let's see, now I'm forgetting which was which. I think, yeah, this was the east hydrograph, this is the west hydrograph. Yeah, it says at the bottom 4C, that was the east one. Down at the bottom 3B, so it's the basin, and then the combined hydrograph together 7,000, and the peak of 900 minutes is kind of in the middle because it's an additive thing where you can consider these as its time and flow rate, and if we had an Excel spreadsheet and you were adding the flow rate from one watershed and the flow rate from the other, then this hydrograph on the left would be the sum of the two. But again, what I want us to do is simulate, like we close all those hydrographs, and in fact let's delete them. So here under hydrographs, delete all. Let's get rid of those. What I want to be able to simulate is how long does it take for the water to flow from 4C towards 3C. So let's open up the HEC-1 parameters again and try and get into that reach. So right now we're looking at 4B. Click Next Hydrograph Station, and this is the order that it goes through. You know, we cycle through is a little bit confusing sometime, but I think if we're starting in 4B, then the next hydrograph station is our reach. So click on Routing Data, and what you're looking for is inside of the window at the bottom. It should say 4R. Let's open up the routing data, and where it says no routing, it has a several different approaches for calculating the flow through the channel. And kinematic wave is one where there's a kinematic wave method for overland flow, but there's also kinematic wave through a channel. And if we select that kinematic wave, you'll notice that it's already filled in data for how long this stream is, and this is the length of the channel that connects 4C and 3C together, and so that's 40,000 not square feet, that's a length, so 40,000 feet. And so, you know, if it's 5,000 feet in a mile, we're looking at about roughly 8 miles of flow distance between 4C and 3C. And then the slope, it's a very, very flat slope, 0.000673. So this is going to be pretty slow moving water with that kind of slope. Now what it doesn't know, it can't get from the GIS data what would be an appropriate N value to use there. So you'd have to actually visit the site and kind of with your eyes verify what kind of a roughness you have in that channel, and most likely with a slope that shallow it's probably just mud lined at the bottom. It's probably clay and sediment, and there may be a handful of places where there's a durable rock. But let's use an N value of 0.03, and then what we also have to do is we have to approximate what the channel looks like. It could use a trapezoidal channel, a circular channel. And let's assume that it has roughly a trapezoidal shape, you know, flat across the bottom and then side slopes. And I mean, unless we go into the site and actually look at it and measure how wide is the channel, we don't know exactly what to put as the width of the channel. But for that big of a watershed, it's probably a pretty sizable channel. I'd say that maybe an appropriate starting point for us would be to say that we've got a 20-foot width, and then Z is the side slope, what is the horizontal to vertical ratio. And so if we say that it's 2, then that would give us 2 horizontal for every 1 vertical. Alright, and so now you can just click OK. And so now we've defined the geometry in 4R. And I don't think previously the symbol for 4R was up on the screen, but now it is. If you look between 4C and 3C, now it says 4R actually on the map. And I think that just came up when we defined the channel characteristics, like, you know, once we told it to enable the kinematic wave, trapezoidal, and that sort of thing. So we're done. We can click done, and we're going to run HEC-1 again. So on the menu across the top, click run simulation. OK. And normal operation. As soon as we click close, it's going to bring up the hydrographs. And so we get those same hydrographs that we saw before, but then now there's also one more. There's a hydrograph added to the reach itself. Let's just open up to verify, for example, that that the hydrograph at 4C looks like it did before. And so it does. That hasn't changed. Here's the hydrograph for 4C. And hydrograph for 3B looks the same as it did before. But what will be a little bit different, I think, is 3C. If I double click and open that up, then the shape of that hydrograph is definitely different. There's kind of like a distinctive point at which the two are being combined. We didn't previously see on the leading edge, as that flow is going up, the time to peak is delayed. It's now 945 minutes, and our previous time to peak was earlier than that, because what it's done is this hydrograph is coming into the point of where it's combined. It's arriving at 3C later than it did before. So we can open up this hydrograph, and this is showing when it's arriving at 3C. So there's so many hydrographs on the screen right now. Let me close some of these. So the only one that's open right now, this hydrograph I opened for 4R, and it's showing when does the water that arrived from 4C, when does it get to 3C? And so it's arriving at 3C with a peak of 975 minutes. And the shape of that hydrograph is also different. If we just compare it, the shape of the hydrograph is slightly different, having to do with the effect of flowing down through the channel. It's kind of attenuating the shape a little bit. And so, you know, we could delete those hydrographs and change the characteristics of the reach. So I can open up the basins and skip over to the reach, and if we wanted to iterate a little bit and try other methods, you could try Muskingum-Kung. But, you know, for instance, how sensitive is this to the roughness of the channel? We could say what instead if it was 0.045 for the roughness, and click OK. So now we have a different Manning's roughness. 0.045 is more rough. That should make it delay more. And we can run the HEC-1 simulation again. and then as soon as it finishes, it will open up the hydrographs, and now we're beginning to see that the two hydrographs come together even more distinctively, and so that bump on the leading edge is bigger than it was before because the delay is longer. With more roughness, it's moving more slowly through the channel. And I could even make it more extreme, delete these hydrographs, open up the basin, go over to the reach, and let's say it's really rough, 0.085. Okay, and then let's run the model. And now at this point, there's two distinct peaks. There's the peak of the watershed 3B arriving out the outlet, and then it starts tapering downward before the peak from watershed 3C arrives. And this is a great illustration of how assumptions can have such a big impact on the output of a model. If we're just guessing at what the roughness value might be for this location, then it's going to have a real effect on the output that we see. One last thing I want to show you is how you can make the simulation run a little bit longer, because right now the hydrograph terminates before the flow gets back down to 0, and that's because we're only doing, I think, probably 100 ordinates, as they're called. And so if you close this, and let's delete the hydrographs that are previously in the memory, so delete all. In the HEC-1 menu, there is a drop down here called Job Control. And if you open up the Job Control, you'll see that right now it's doing 15-minute increments, and it will run 100 times. And we could change that to 200 times. Okay, so click OK after you change it to 200, and then run the simulation again. And if we look now at the hydrograph, we've got enough duration to our model that it gets the flow rate down to 0. So we've got the entire event. For a large watershed, if the storm duration is 24 hours, then you may need more than 100 ordinates to get through the entire cycle of it finally draining the watershed. So are there any questions, any steps that I went through too quickly that I need to illustrate again before we part ways for today? So just to remind you, the applicable homework component that goes with what we are doing today is to pick a watershed that's interesting to you anywhere in the United States, and it should be at least 1,000 acres, and subdivide that. And so you're going to be running a HEC-1 model on the 25 and the 2-year storm with a single basin, and then go through the process of subdividing it. And again, I ask you to submit your work in the form of creating a guide for yourself, and so not just screenshots that showed what you did, but also kind of an explanation, so that 3, 4, 5 years in the future, when you need to refresh your memory on how to use WMS, you've got that available as a resource. So that assignment is going to be due on the last day of class, Friday the 24th. That's it for today. Feel free to send me any emails if you have a question, but thanks for being here. Hope you're doing well, and I'll see you on Friday.